You'll see today's aim is that we're going to be using commutative property and combining like terms to simplify expressions. So really this is something that you have already done before. We're just going to be taking it to the next level. And that's a lot of what 7th grade is. It's taking things that you already know to the next level, or taking several different things that you already know and putting them together. That's what we're going to be doing today. All right. So looking at this, the first question that I ask you, it says if you have 4 apples that weigh X pounds and 5 oranges that weigh Y pounds each, write an expression that represents their total weight. I actually want you to do that independently on your own. Write an expression that represents the total weight of the fruit in this problem. 4 apples that weigh X pounds each, and 5 oranges that weigh Y pounds each. Somebody share out. Judea. Yep. 4x plus 5y. Okay, Judea, I've got a question for you. Why didn't you put that together? I mean, it's 9 pieces of fruit. Why didn't you just put like 9x or 9y? Different species. So you're going back to some of that language that Ms. Wilcox introduced to you last year. She's talking about apples and oranges being different things. So if we're talking about the weights of apples and oranges, they weigh different things. We can't put them together. We can't say this is 9 fruit. The weight of the 9 fruit is blah, 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 because they have different weights. We have to describe them differently. So that's going back to that idea of unlike terms, which you guys call different species. Okay? So let's quickly come down here and let's go with this definition. I hear Judea saying these are unlike terms. What does that mean? What's our definition for unlike terms, Mr. Resendez?
Like they can't be combined.
So they can't be combined. So this is definitely one important point about unlike terms. They can't be combined. And how do we know 2 terms are unlike terms, Emmanuel?
They're different species.
They're different species. What does that mean more mathematically? We've got to step out of our comfort zone a little bit there and start using some of that mathematical language. What does that mean more mathematically? They're x and y. Let's be more general even than that. X and y are both what? Variables. Their variables are different. Unlike terms, can't be combined. They have different variables. Before we move on to like terms, let's come up with some examples of some unlike terms. For example, Craven.
Okay. So 32s times
32s and 32s and 5y. I'm not going to put any operations in between. I'm just going to talk about them being different terms here. All right. Let me come up with some different ones that might spark your interest. 5x and 5x squared. Kip yes or kip no. Are these different terms? What's different about them? What makes them unlike terms, Sage? Yeah, so if we're thinking about these different variables, if we were plugging in values here, this x squared is going to be worth something different than this x. So that's why they're unlike terms, is because their variables have different values. Okay? So this is an example of unlike terms. How about this one? Are these like Kip yes or kip no. Are these unlike terms? No, these are actually like terms. The reason I put that one up there to make the point, a negative coefficient, or the coefficient has nothing to do with it. So this doesn't belong there. That belongs up here with our like term examples. 5x and negative 3x. All right? I hope you were paying attention and that you erased and put that in the right place. Let's try this one. 3xy and 4x. Kip yes or kip no. Are these unlike terms? Yeah, so they have different variables. They have one variable in common, the x, but this one has an extra variable. So this xy is going to be worth something different than just that x. So these are unlike terms. Cool. So let's move back up to our definition of like terms. Unless Kyrie had a question first.
If you had, like for example, if there was something like 3xxxx plus 4xxxxxx, would it be the same even though it's more x's?
So if it has more x's, remember that you would combine those x's into something like x cubed and x to the fourth. But to answer your question, either way you look at it, they are different terms. All right, so going back to like terms, unless Brenda had a question.
How about if we undo the exponent from the 5x and 5x squared? If we undo that one, can we just add 5x plus the 25x?
So she's saying if we broke this down, this would be like 5x and 5x times x. So what we see here is that these are definitely different. This has a different set of variables than this set. And this is, for some of you, this makes it more clear to you why these are unlike terms. They have different set of variables. X times x is going to have a different value than x. All right. Now let's go to like terms. Judea, what was your definition that you had for like terms? Okay, so these can be combined. And sorry, I interrupted you. What was that second part you said? Have the same variables. They can be combined and they have the same variables. Variables. So, let's come up with some more examples. Let's come up with some interesting examples. I've got a very basic example up there already. Fraven.
5a plus 12a.
5a and 12a. I don't even need the plus in there. We're just gonna talk about terms right now. We'll talk about addition of them. 5a and 12a. What about 3xy and 4xy squared? No, that doesn't work because with that y squared in there, that means that we have something different. But I can't switch that to 3xy and 4xy. Kip yes or kip no, would these be like terms? What about 4x squared and 5x cubed? Cubed to the third power. No, okay, you're telling me no because those don't have the same variable. It's got to have the same exponent, okay? So that's what we're talking about when we're talking about like terms. Questions about like terms and unlike terms? Leslie.
So the like term, you can add them together and they still make the same value?
Yeah, so then we're going to be talking about combining like terms. We're going to do that in some examples over here. This is something that most of you are already familiar with. So when we're looking at this example, we're going to think about a handful of things that we just absolutely have to do. These problems are probably the most detail-oriented problems that we will do all year, which is crazy because we do some pretty detail-oriented stuff. There are a lot of things that we have to think through here first. Now, when I look at this problem, I see that there's an exponent. We have said before that we can't leave, change, switch when there are exponents involved. But that exponent is clearly attached to a variable. If that exponent is clearly attached to that variable, we can go ahead and leave, change, switch. Okay, so the first thing that we're going to do, we're going to leave, change, switch. So I have leave, change, switch this. To adding a -4. Another thing that we're going to do, since we're going to be talking about combining like terms, all of you already know that the process of combining like terms requires you to add coefficients. Well, I see two numbers here that don't have coefficients. What are we going to do about those two variables that don't have coefficients? Iron. I don't want to combine them because the two variables that don't have coefficients, they're not like terms, so we definitely can't combine them. What are we going to do with them, Judea? One more time. I still can't combine those terms because these don't have the same variables.
2xx.
So what do I need to do with these two terms that have? I am asking you about these two terms. These two terms don't have coefficients. Somebody please tell your teammates, what does that mean that those two terms don't have coefficients? Okay, check back to me. 5, 4, 3, 2, and 1. Marbella, what does it mean that those two terms don't have coefficients? Ow! They don't have a value. They don't have a number in front of them. There's nothing being multiplied in front of them. But we know that something really is being multiplied in front of them. Andrea, it's a 1. So one thing that we're always going to do is we're going to add that coefficient in front of there. Because one of our steps to combining like terms is to add coefficients. Well, if it didn't have a coefficient, a lot of us just wouldn't add anything. We would add it like it was 0. Okay? So the next thing that we're going to do is we want to get all of our like terms next to each other so we can combine them. There's a very special way that mathematicians do this. They always start with the variables that have what we call the highest order. That means they have the largest exponent. So they're going to move this term, 1x squared, to the front. As I was saying, we move the term that has the largest order, the highest exponent, to the front. What did I just say?
Highest exponent to the front.
Highest exponent to the front. I'm going to cross that out as I go, and this is an important piece of work. Why would it be important for me to cross this out after I've moved it? Maria?
Or you won't get confused later.
Yeah, so I don't get confused later. So I don't write it again. So I can go back in my work later and be like, I did rewrite that. All right? So next is the variables that don't have exponents. If there are multiple variables that don't have exponents, we put things in alphabetical order. In this case, we just have the x term. So I'm going to move this 2x. and this 1x. Finally, I end with the constants. Remember, constants are terms that have no variables. They always go last. So I'm going to put my 3 here and my negative 4 here. What property did we just use? Somebody with a raised hand. What property did we just use, Judea? This is the commutative property. I would get into the habit, when I write things down like this, that you do the same thing. It's not necessary for you to get the right answer to this problem. However, you will be tested in a way that you will be asked to explain and describe why you did certain steps. Okay, looking at the next step, now we can go ahead and combine our like terms. We're actually going to use the associative property here. So I'm going to group my like terms next to each other. And when I add like terms, I add the coefficients and the variable stays the same. So for instance, this 1x squared, it doesn't have anybody to combine with, so he's just going to come straight down. But these like terms, 2x and 1x, I add the coefficients. 2 and 1. 2 plus 1 is 3, and the variable stays the same.
How do you do this?
Leslie.
Why does it not become 3 and 2x?
So when we think about that, that was going back to our original problem. Let's say I added 2 more apples to the mix. I would be adding 2x. Now, if we think about how this works, this is saying 2 apples plus 4 apples. If you make it 6 apples, is that going to make sense? No. And mathematically, that wouldn't make sense either. If we think about these as weighing 2 pounds each, this would be 2 times 2 plus 4 times 2.
So you don't double the apples?
Yeah, you don't double the name. The only thing that you're doing is you're adding the coefficients. Coefficients only, variable always stays the same. All right? And then we're also going to use associative property to group these two, 3 plus negative 4. This is opposite sign subtract, and we need to take the sign of the larger number. So if you remember way back in the previous unit, at the very beginning of the previous unit, I said it's imperative that we are able to add, subtract, multiply, and divide integers and have it perfect every time. This now becomes a very small step of a much larger problem. Okay? There's one last thing that we're going to do with any of these problems when we're simplifying them, is there are actually simpler ways to write this. And this is what I call kind of cleaning up the mess. There are some extra things here that we can rewrite even more simply. So, looking at this 1x squared, is there a simpler way I could write 1x squared? Kyrie?
2x.
Is 2x, 2 times x, the same thing as x times x, which is x squared?
Yeah.
No.
No.
Is there a different way to write 1x squared? Sunny. X squared. Remember that we can rewrite that. It's the same thing. 1 times x squared, just x squared. That's the identity property. So we added that on earlier in case we needed to combine like terms, but we don't need it at the end. It's implied. We also run into there's a simpler way to write this plus negative 1. And one thing that you don't know about leaf change switch is that you've always used leaf change switch to take subtractions and turn them into adding negatives. Well, we can switch it the other way around. We can take it from an adding a negative and we can switch it back to a subtraction. So if I leave change switch here, leave change switch, that's going to give me change to a subtraction, switch to a positive 1. So what we've done here is we've taken what used to be 3 symbols plus negative 1, and we've simplified it to 2 symbols, minus 1. It's a very small detail, but they're the same thing, and you have to know that you can do that. As far as I'm concerned, if I ask you a problem and it is open-ended, you must leave change switch all additions of negatives back to subtraction for your final answer. You must also take away all of the coefficients of 1 because they are not necessary. That's simplifying. So our goal today is to simplify expressions. And the reason why we do this is if you're thinking like a scientist, you're going to probably end up with an equation like this at some point. And you're going to be going through, and a lot of times you're going to be plugging in the many different values of x. Well, it's a lot easier to plug it into this equation than it is to plug it into this equation. This is less work. So a scientist will do this work one time to save him the work 20 other times. Okay? Questions about this first problem? Kyrie.
Is it a necessity to put the 1x in the front? Like, do you have to, or it's something that you just do?
Mathematicians, it doesn't change the value. Thinking about it in commutative property, we can move them around in whatever we want. But mathematicians will always write equations in this way, with the highest order first, then the regular variables in alphabetical order, then the constants last. Carson.
I don't get how we put it in order.
Okay, well, we'll look at one more example. Let's see if maybe that will help out. Okay? So the next one. The first thing that we need to do is we need to look to see if there are any coefficients that need to be added here. Kip yes or Kip no. In this problem, are there any coefficients that need to be added? Any coefficients of 1 that we need to throw in there? That was a Kip yes or Kip no question. I'm seeing about 3 people respond. Kip yes or Kip no. Are there any variables that need a coefficient of 1 added to them? Okay. So there are no lone variables here, so that means the next thing that we need to worry about is doing what? Maria? Leave change switch. After we do the leave change switch, then what? Kevin?
Why did I leave change switch and then the x, the 3, negative 3x with the negative 3x?
Okay, so he's commuting his like terms. Now, he's talking about the order that we want to commute them in. Are there any terms that have exponents for their variables? Are there any terms with exponents on their variables? Okay, no. So we don't have to worry about that. The rest of them we need to put in alphabetical order. So we have x terms and we have xy terms. Alphabetically, which comes first? X. This is like trying to alphabetize the word A and the word AN. Okay, so our negative 3x is going to come first. Plus another negative 3x that I see over here after the leave change switch. And I'm out of x terms, so I'm now going to move on to my other variable terms. Negative 6xy. That's my only xy term, so now I'm going to move on to my constants.
30.
Plus 30.
Plus 2 plus negative 2 plus 2. I think.
Plus 2 plus negative 2. So now we have used the commutative property. We've moved our terms around. What are we going to do now?
Do something.
We're going to answer Judea's question. That's what we're going to do now.
See, I'm
Yes?
doing something.
When we do negative 3x plus negative 3x, we get x or just
So, Judea is moving on to the next step. She was actually answering questions. She's saying she's going to combine like terms here. Negative 3x plus negative 3x. So our rule is to add the coefficients. Negative 3 plus negative 3. Like signs add or opposite signs subtract. Like signs add. So that's going to give me 6. Take the sign of a larger number. That's negative 6. X. Right? And now we're going to move on to our xy terms. There's nothing to combine there, so it's actually just going to come straight down. And now I'm going to start combining my constants. Now, somebody did something interesting in the previous class. They recognized something about our constant terms. Is there anything you notice about our constant terms that's going to make the math on this easier if we do it a certain way? Ian? Yeah, we have an additive inverse over here. So these additive inverses, 2 plus negative 2, add up to 0. Which leaves us with just the 30. So that saves us a little bit of time. Now there's one thing that we have to do at the end. We have to clean it up. Our little math janitor is going to come along and he's going to say, are there any coefficients of 1 to get rid of? No. And then he's going to say, are there any additions of negatives that we need to get rid of?
No. Yes. No.
Okay, I'm going to look through. Here's an addition, there's a negative. That's 1. Here's an addition, that's a positive. So we have one that we need to leave, change, switch. Back to that subtraction, because we're going to clean it up just a little bit. So the negative 6 is left. We change the addition to a subtraction. We switch the negative 6xy to a positive 6xy. Then we add 30. Okay? Questions?
Nope.
Okay, let's move on to those key points really quickly.
Oh, we did finish.
Judea? What? Always simplify. What do you mean? All right, so she's saying clean up at the end. By dropping coefficients of 1. And leave, change, switch, adding negatives. Leave, change, switch, adding negatives to subtraction. Leave, change, switch, adding negatives to subtraction. Other key points. Emmanuel.
Don't forget to pay the math janitor.
What is the math janitor? Huh?
Yes. All right, Leslie.
Oh.
Okay, so she's saying as one of the setups, I actually think that what she's getting into is about to be a list of steps. So I think for our second key point, I'm going to move it over here so we've got space to do it. And she's starting with some steps here. And she's saying step 1,
Step one.
add coefficient of 1
One.
to our lonely variables. To our variables that don't have coefficients.
Step two.
Step 2, what did we do next? Judea. Even before we used the commutative property, we needed to do something else. Yeah, leaf chain switch. Then use commutative property.
Use commutative property. Step three. Use
To put like terms together. After we put our like terms together, what do we do after we put like terms, or after we've commuted our like terms together? What do we do after we have commuted our like terms together? Relax. You're freaking him out.